technical session, not of the current submitted paper, but a paper that was submitted nearly a decade ago. And a very competent committee of Chanchal Roy from Saskatchewan, Canada, and Vasudeva Varma from IIIT Hyderabad were the review members for the Test of Time Award. And it's my pleasure to introduce Dr. Jitendra Singh Thakur for the Test of Time awardee. And this paper is co-authored with Dr. Atul Gupta. I think when Dr. Jitendra was pursuing his PhD at IIIT DM in Jabalpur. So currently he teaches at Jabalpur Engineering College and kindly agreed to come all the way from Jabalpur. So over to you, Dr. Jitendra.
Thank you. Good afternoon, everyone. So, as ma'am introduced, I am associate professor at Jabalpur Engineering College in Computer Science and Engineering Department. I am also heading that department. And this paper I published in ISEC 2014 when I was doing my PhD from IIIT DM Jabalpur. So, it's about generating sequence diagram from use case specifications. I am thankful to the organizing committee as well as the steering committee for choosing this paper for the Test of Time Award. So, so this is the content, motivation, related work, proposed approach, tool support developed, evaluation of the approach, conclusion and references. So, what is analysis modeling? It is about identifying problem level objects from the software requirement specifications. Then what we do, we identify the interactions between those objects, and we at the analysis level, we develop analysis class diagram and sequence diagrams. There are other diagrams also, activity diagrams and state transition diagrams that we develop at this analysis level. So, my this work is focused on generating sequence diagram. So, what is the motivation behind this is the transformation of UCS into the analysis level sequence diagram. It is normally done by the human analyst, and this take lots of effort and time. And it becomes, sometimes it becomes the requirement specifications, they are, as they are ambiguous and different analysts, they can derive the analysis, different analysis model. So they can read these specifications in different manner. So they come up with different kind of analysis models. So this tool support, it can correctly transform the UCS into analysis model. It saves lots of effort, time and money. So this was some related work. So there were some semi-automated approaches that that can generate these analysis sequence diagrams and analysis level diagrams from software requirement specifications. So each of them, they have some limitations. So this is my work. So what we do is we read the use case specifications which are written in English language, and what we do, we use Stanford natural language parser to obtain POS stack type dependencies and parse tree from the sentences. What we do then, we have created sentence structure rules and transformation rules, which are key in this approach. So what they do is, first we identify the type dependencies. So we read the use case specifications. So in our that paper, when we wrote that paper, so the use case specifications, they should be written in using simple sentences, except for a few complex sentences that are joined by coordinators, if, else, while and that. So a simple sentence consists of only one independent clause, whereas we have different kind of sentences, compound sentence, complex sentences. So these compound sentences are sentences, they are joined, we join two independent clauses using coordinators, these for, nor, and, nor, but, or, yet, so. So these are compound sentences. We also have complex sentences. The complex sentences consist of one independent clause and one or more dependent clauses. They are joined using subordinators such as because, since, although, when, and others. So what we do, we read these simple sentences. We read the sentences from use case specifications. Then what we do, we use the Stanford NL Parser API to identify these type dependencies, POS tags and type dependencies. Suppose this is an example of a sentence that we have taken from a use case specification validate pin of ATM, right? So the sentence is the system reads the ATM card number. So this is a very simple sentence. The system reads the ATM card number. So when we give this sentence to Stanford NL parser, it generates these POS tags and type dependencies. These are nothing but the parts of speech tags of these sentences. For example, the is the determiner in this sentence, है ना? System is the noun, reads is the verb in third person. So these are the parts of speech tags, and these are the type dependencies. So these type dependencies, they represent semantic relationship between the words in the sentences. So for this sentence, the system reads the ATM card number. So these are the type dependencies which are generated. So type dependencies, these are the triplets. It has TD name, head word, and dependent word. So this TD name, it represents the name of the type dependencies, and head words and the dependent word. So there is a relation and subject. That means this head word read, its dependent word is for this dependency is system. That means it represents that system is the subject of the verb reads in this sentence. So system is the subject, and this dependency we can see that number is the direct object of reads, right? So the system reads the ATM card number, so number is the direct object, system is the subject of this sentence. So we get this relationship from type dependencies. Here also in one more example I have shown, the system reads the ATM card, ATM customer, sorry, the system sends the ATM customer an SMS, right? So for this sentence, the type dependencies generated by the parser is given here in a graphical view. The system sends the ATM customer an SMS. So here we have a verb sends, its subject is system and its direct object is SMS, and its indirect object is ATM customer. So once we generate these type dependencies, we use sentence structure rules that we have created to identify the structure of that particular sentence, right? So these are the sentence structure rules that we have developed. So these are the sentence structures that are identified using these type dependencies. So SVDO, subject verb direct object, subject verb direct object preposition object, subject verb indirect object direct object. So these are the sentence structures that we identify using the type dependencies. So so that we can process each sentence based on its structure, because in a sentence the required information is present at different places in this in it, right? So to correctly extract the required information, first we need to identify its structure. Once we identify the sentence structure, then what we do is once the sentence structure of the sentences are identified, we then we apply the transformation rules. So for each kind of sentence, we have created a transformation rule. So these transformation rules, they help us to extract the required information from the given sentence based on its structure. So these are the transformation rules. So we identify these three kinds of objects: entity objects, boundary objects, and control objects from the use case specifications and its sentences. So what we do, to identify the control and boundary objects, what we do, for each use case, the control class is created from the use case name. So suppose the use case is withdraw funds, so one control class, it is created for that particular use case. For each act, what we do, we create a boundary class for that particular actor. And to identify these entity classes, what we do, entity objects or entity classes, for that we use POS tags. Each tag in the flow sentence, the nouns are stored in a list of nouns. So we extract these from the POS tags of the sentences, right? We store them in a list of nouns. After that, the TDs of each flow sentence in UCS, they are scanned, and the rules written below, they are used to identify the interactions between the objects. Basically, use case diagram is the interaction between the objects. So to identify those interactions, we have written the transformation rules. So suppose this is the transformation rule number 4. So if subject has A, and D object has B, then B is identified as class and A is identified as the attribute of the class. So it basically it is used to identify the attributes of particular class. So for interactions, we have transformation rules which are given below. So these are the transformation rules which are used to identify the interactions between the objects. Suppose this is the transformation rule 12. As for the sentence that has a structure SVDO, so we have this particular transformation rule. Suppose we have these two type dependencies we extract from the sentence: N sub j AB and D object AC. So here we identify source class as the B and the destination class as C. This source class B, it sends the message A to destination class C. So basically message is nothing but the verb present in the sentence. So this verb is identified as message, and the source class is class B, which is sending message A to class C, right? So these are identified. So similarly for other sentence structures, we identify these. For example, we can see one more sentence structure, SVIODO. So here these three type dependencies are important: subject, indirect object, and direct object. So from here we identify the source class, right? And from indirect object we identify the destination class, and this from direct object we identify the message, right? Here it is, I think it is hidden here. So this is sent as a message. So these are the transformation rules that are used to identify the subjects, objects and interactions between those objects, right? So once we have identified those, we generate the SD edit commands. So this SD edit is an open source tool which is used to generate sequence diagrams by supplying it the textual commands. So we can give it textual commands and it generates a nice sequence diagram for that. So, so what we do, we generate these SD commands and we give these commands as input to this SD edit API, and it generates a nice sequence diagram from the use case specifications. So we have implemented this uh, whole approach in a tool, automatic sequence diagram generator. It is implemented in Java using Eclipse Indigo 3.7. We have used the Stanford NL Parser API version 2.0.4. At that time, it was the latest. And we also used Apache POI API to read the UCS written in MS Excel file. So our approach, it reads the UCS use case specifications from Excel file. And we used SD edit version 4.0 to generate the sequence diagram. So we have also evaluated our approach, and there was one existing approach which was generating sequence diagram, that was a tau-ken, and our approach we compared. So it was the tau-u etal paper from which we have compared our approach. So we have taken these three use case specifications because their output sequence diagram as well as the input use case specifications were present in their paper also. So it was the latest paper at that time. So we for generating sequence diagrams, so we compared our approach with that. So after the evaluation, so these were the measures which were used for finding whether the sequence diagrams they are generated, how much correct they are, how much complete they are, right? So these were the measures. So first measure was object correctness, second measure was message correctness, third measure was sequence diagram correctness, fourth measure was sequence diagram completeness. So these were the measures which were used. So measures were incorrectly identified as objects, OCR1, incorrectly named, incorrectly stereotyped, and these are for message, incorrectly identified message, incorrectly identified source object, incorrect target object, incorrect message name, parameter, condition, and for so how we calculate the sequence diagram correctness based on the object correctness and message correctness. If objects and messages they are correctly identified, that means the sequence diagram is correctly identified. And for the sequence diagram completeness, we use this particular measure, the number of flow sentence sections that have not been assigned to any message in the sequence diagram. So how we calculate the this completeness? Suppose we are having 10 sentences in a use case specification. What we do is, for each sentence, we check whether that particular sentence is mapped into a sequence of message or not, right? So if it is not mapped in your diagram, then it is the it becomes the incorrect transformation to the model, right? So it results in incompleteness. Suppose there are 10 sentences in the use case specification. Out of that 10 sentences, 8 sentences they are mapped into the diagram. So the completeness of diagram will be 0.8, right? Or 80%. So these were the results of the evaluation that we did. So it was for this particular use case validate pen, a tau-ken and our approach. So their sequence diagram correctness was 61.8% and ours was 93.7. In case of completeness, 93 and 100. And these are the results. So, so here are the some limitations of our work. So the approach assumes that the sentences in the UCS are correct and unambiguous. So if UCS contains incorrect sentences, so that parser will not be able to correctly identify the type dependencies between the sentences, between the words in the sentences. So it is must that the sentence should be correct, grammatically correct, right? So and it should be unambiguous also. Otherwise, we are not able to solve this problem till date. Natural languages are quite ambiguous, you know, whereas our programming language they are unambiguous. So another limitation is compound sentence and complex sentence. So at that time we were only able to process these simple sentences and only few complex sentences that contains if, while, and those kind of sentences, right? Co-reference and pronoun resolution was also not addressed in that approach. So we used Stanford parser and its accuracy for POS tag was 97% and its accuracy for type dependencies was 84.2%. For all kind of sentences, they have evaluated. But in our case, as we were giving only the correct sentences as input, and most of the sentences are simple sentences, so our approach is able to get more accuracy as compared to this base accuracy of the Stanford NL parser. So future work, so how to tackle ambiguity in the languages and inconsistencies in UCS. The works, more work can be done on these. To handle compound and complex sentences, to handle core reference or pronoun resolutions, extend this approach to generate other UML diagrams and to improve the accuracy of type dependencies. So, so this is all our work. So these are the references. And one more extension of this work that we presented in, it was automated software engineering conference at Singapore, which was held during September in 2016. So it was about identifying class diagrams from use case specifications. So earlier we identified, we have generated sequence diagram, and this was about generating class diagrams from use case specifications. Okay, I can show the tool that we have developed because we are short of time. So this is the tool support that we developed, and it how it works. So to read use case specifications, what we do, we can select any use case specifications. So it is identifying the type dependencies and POS tags. So here for this particular use case specification, withdraw fund, it has identified the sentence structures. So sentence type and subtypes. So types of sentences, we can classify the sentences into statement, interrogative sentence, declarative sentence or statements, interrogative sentences, exclamatory and command, right, or imperative sentence. So, and again, we can again subclassify them into simple sentence, complex sentence, compound, and compound complex sentences. After that, what we do is we identify the structure of those sentences, and once the structure is identified, and we have we can apply these transformation rules to generate the class diagram. So it is the class diagram generated for that particular UCS, and this one is the sequence diagram. So I think it is visible, quite visible. So these are the objects which are identified, and these are the message sequences between these objects. So it generates automatically it generates the sequence diagram from the use case specifications. So, thank you. Any questions?
So, if GPT-4 was available to you at that time, would you have still bothered to do this?
No, I think so. We could have used that functionality to we can do that in lesser time, and we can prepare some better model.
After your PhD, did you still try something on this, or just left it as a PhD?
I am working on some other problems, but I am planning to use that ChatGPT to achieve some better results.
What have those papers done in terms of extending your work, or what kind of research has been done subsequent or built on top of your work by the other researchers who have referred to your paper? So can you elaborate a little bit on that part?
They have not developed any tool support, but they are working on some problems. So they are comparing this work. So some case studies have done, some reviews they have been done, but they have not yet given any tool that we gave at that time.
One is that, isn't it a nice thing, publish your paper in ISEC, and after a couple of years, publish an extension of that paper in ASC, FSC, or ICSE, and that's what Dr. Jitendra has done. So here is all to the young researchers and PhD scholars to start publishing in ISEC, and then, head upwards for ASC, FSC, or ICSE. So please do send more of your submissions next year to ISEC. And the other comment is with reference to morning's invited talk. So here is a PhD tool that works 8 years after PhD, right? The tool is still working, right? So I think it deserves the best paper test of time award. And
Thank you.
so may I request RD to come and hand over the certificates, please?